Hey everyone, here's our third example problem for static equilibrium. This is the ladder problem. So for this problem, we have a 25 kilogram, 6 meter long ladder that rests against a smooth wall at a 35-degree angle with the ground. If the coefficient of friction between the ladder and ground is 0.45, how high up the ladder could a 50 kilogram person walk up so that the ladder does not slip? Assume there's no friction between the wall and the ladder. Okay, so for this problem, just like all of our other static equilibrium problems, we're going to start with a force diagram, and I'm going to draw it right on this picture. So I know that at the bottom of the ladder, I have the normal force pointing up. Okay, then for my force friction, I have to think about if the ladder were to slide down, that would mean the bottom would slide back this way, which means my friction force is going to point this way against the motion or the potential direction of motion of the ladder. Then I know I'm going to have a force from the wall pointing out this way. And then I know for the force gravity of the ladder itself, that's going to be at the center of mass, which is going to be about halfway up, or not about, it will be halfway up. So that looks about halfway up to me. So that's going to be force gravity from the ladder. So then, since I don't know where the person is going to end up along the ladder, I'm just going to put the force gravity of the person just somewhere on the ladder. The big thing later on when we go to look at the torque that the force gravity from the person could produce is making sure that it's the force gravity from the person is pointing in the right direction. Which doesn't really matter where you put it, the direction of the force won't change. So there's my force diagram. So I'm going to write a net force equation for the x and y direction to see if there's anything that I can calculate right away that could help me get the value of the height that the person could climb up. So my net force in the x direction, I'm going to have the force friction minus the force from the wall equaling 0. And in the y direction, I'm going to have the force normal minus the force gravity from the ladder minus the force gravity from the person, also adding up to 0. So right now I see I have force gravity of the ladder, I have force gravity of the person. I can solve for force normal, which means I can solve for force friction, which means I can solve for the force of the wall. So right now I can get all the forces that I need to help me find the distance that the person can climb up, because to get the distance that the person's going to climb up, that's going to come up in my torque equation. So let's see, I'll start with force normal. So force normal will really equal just force gravity of the ladder plus the force gravity of the person. The force gravity of the ladder will be 25 kilograms times 9.8 newtons per kilogram, and that will be about 245 newtons. Plus, the force gravity of the person will be 50 kilograms times 9.8 newtons per kilogram, and that will be about 490 newtons. And so the value of the force normal will be 735 newtons. And then I can calculate force friction because that's just equal to the coefficient of friction times force normal. So 0.45 times 735 newtons will give me 330.75 newtons. And then from my net force equation, I know that the force friction is equal to the force from the wall. So I'm just going to throw that equal sign there. All right. So now I have all the forces that I'm going to need for my net torque equation. So when I think about my net torque equation, I have to think about where am I going to put my axis of rotation. So since we know the forces or the value from all the forces, we have to think still about where's the most advantageous place or beneficial place for us to put the axis of rotation. And I think that the best place for the axis of rotation is going to be down here at the bottom, because even though we know the value of the force normal and the value of the force friction, it's easier if we can eliminate two forces and just work with three forces here instead of two forces in the same spot. So I'm going to look at, so now I'm going to focus on the force from the wall going this way, force gravity from the ladder going this way, and then I'm going to draw the force gravity from the person up here for some of the other things that we're going to end up drawing. Okay. And so then I'm going to figure out which way are they going to cause the ladder to rotate. So if the force from the wall is pushing this way, that would mean that it's going to cause the ladder to rotate this way, which is counterclockwise. So the force from the wall is going to cause it to go counterclockwise, which is going to be a positive torque. And then the force gravity from the ladder and the force gravity from the person are both pulling down this way, which would cause the ladder to rotate this way. So the force gravity from the ladder and the force gravity from the person are both going to cause a clockwise or negative torque. Okay. And so then my net torque equation will be equal to the torque from the wall minus the torque from the ladder minus the torque from the force gravity of the person, and that will all add up to equal 0. Okay, so now what I'm going to do is I'm going to expand this out. So I know for all of these forces, if I look at my ladder, all of these forces are being exerted at an angle relative to the positioning of the ladder, even though they look horizontal and vertical how I've drawn them. So I need to think about, for all of these torque equations, I need to find the perpendicular component of each of those forces relative to the ladder. Okay, that to me personally is really the trickiest part of the ladder problems. It's all the same stuff with the net force and the torque, but the angles can be a little tricky. So for my torque from the wall, I'm going to expand this just out to be the force from the wall, the perpendicular component, times the distance of the wall from the axis of rotation, minus the force, the force gravity from the ladder and the perpendicular component of that relative to the ladder, times the distance of the ladder from the axis of rotation, minus the perpendicular component of the force gravity of the person, times the distance of the force gravity of the person from the x-axis. Okay? So in determining the angle, one of the things that we can look at, so again, we're looking for that perpendicular component of the force relative to the ladder. So I've tried to draw that. So now, if you remember from all the ramps that we've done in all of our Newton's laws problems, we can think of just like how we would find the components of the force gravity when we were on a ramp. So if this angle here, what was it, was 35 degrees, that means the triangle made here and here are similar triangles to this triangle. So we're going to have 35 degrees here and 35 degrees there. I know that's kind of hard to see, sorry. Okay. Now for the wall, our perpendicular component for the wall is going to be here. Okay. And now if I drew all of the geometry and everything for this angle is actually going to end up being 55 degrees here. Okay. Sorry. Let's see. Okay. And so, and I can look at that if I did, here's like the force gravity from all of the RAM problems and everything. If here's my component, that would be 35 degrees here, right? 35 degrees would be there, which means 35 degrees would be here, there, which means next to that to make 90, that would have to be 55 degrees. So I know that's not the best drawing, and my lack of being a math teacher makes that a terrible explanation, but hopefully that makes sense. Okay, so now I can start plugging in everything. So my force from the wall, I already know the value of that is 330.75 newtons. So I'm going to do 330.75 newtons times the cosine of 55. And then the distance from the axis of rotation is going to be 6 meters. Minus the force gravity from the ladder we found was 245 newtons. And we want the perpendicular component, so times that by the cosine of 35 times the distance from the ladders from the axis of rotation. That's going to be halfway, so that's going to be 3 meters. So I ran out of room. And so then minus the force gravity from the person we found was going to be 490 newtons. and then times the cosine of 35 to get its perpendicular component. And then since we don't know where the person can be, we're just going to put an r there, and that should add up to equal 0. So then when I do all the algebra, the torque from the ladder ends up being about 1,138.26 Newton meters minus the torque from the ladder, which is about 602.08 Newton meters, minus 490 times the cosine of 35 ends up being 401.38 newtons times r, which equals 0. These two subtracted, I get 536.18 Newton meters minus 401.38 newtons times r equals 0. Then when I add that over and divide, I get that the distance the person can go up the ladder without it slipping is 1.35 meters. Okay, so hopefully that helps with the ladder problems. Again, the force part of it and the torque part of it isn't changing, but the angles can be a little tricky. So hopefully the pictures that I drew for the angles are okay. But of course, if you have questions, let me know and I'll answer them. All right, thanks guys. Bye.